In this module of Chapter 3 on mortality, Module 3.5, I will describe mortality models used in demography, including why they are important and 7 of the best known ones. There are 3 principal justifications for postulating in an analytical form for mortality and survival functions. First, many phenomena in the physical sciences can be explained efficiently by simple formulae. Therefore, some scientists have suggested that survival in both humans and non-human species is governed by simple laws. Second, it is easier to communicate a function with a few parameters than it is to communicate a life table with several hundred parameters and probabilities. Finally, a simple analytical survival function is easily estimated using a few parameters from the original determination of the mortality data. Here I will describe and briefly discuss a number of the more prominent, better known, and/or useful mortality models in demography. I will name the model, show the mortality formula and the survival equation, and make brief comments for each. The first model in this collection of models is the Moivre Model. I include this model not because it is realistic or used by many demographers, but because it was one of the first models to attempt to describe age-specific mortality. Mortality rate in the Moivre model equals the inverse of the difference between the maximal and the current age. It tends to unity as age approaches a maximum. The survival schedule is a linearly decreasing function of age from 1.0 at age 0 to 0 at the oldest age. The advantage of this model is it's simple, it's transparent, it's easily understood, requires only a single parameter, and produces a linear survival function. The assumption that survival is linear with age is often applied over short age intervals. Next is a Gompertz model. The assumption of this important model is that mortality beyond the age of sexual maturity or another predetermined age is an exponentially increasing function of age. The mortality trajectory for the Gompertz model is exponential, and its survival trajectory is sigmoidal. This model contains 2 parameters. Initial mortality rate A, which denotes mortality at the youngest age class in the specified age interval. The exponential rate of increase in death rate B is the second parameter, and it denotes the age-specific slope of the mortality function and is often referred to as the Gompertz parameter. The Gompertz model provides 2 useful formulae. The mortality doubling time, denoted MDT, defined as the time required for the mortality to increase by 2-fold. This is the formula. The estimated maximum lifespan is the second formula. It's denoted Tmax, and it's defined as the age when a population subject to Gompertzian mortality rates has diminished to 1 survivor. In the following graphs, I show the effect of different values of the 2 parameters A and B on both the mortality and survival trajectories. We have age on the x-axis of these graphs. The first shows the effects on mortality and survival trajectories of parameter A in the top 2 graphs. This graphic shows mortality schedules that differ in initial level due to the values of A, with the black line on top representing the schedule with the highest initial mortality, and the gray line at the bottom representing the schedule with the lowest initial mortality. Mortality in each of these schedules is increasing at exactly the same exponential rate B. The corresponding survival curves as the outcome of these different mortality levels are shown here, with the shortest lived in black and the longest lived in gray. The survival differences are scaled to the right as survival increases with the reduction in mortality. Now we see in the bottom set of graphs mortality schedules that differ in their rates of increase with age due to differences in the Gompertz parameter B. Note the starting point in the initial mortality level, that is parameter A, is identical in all 3 of these schedules. The schedule with the highest rate of increase in mortality with age is shown in black, and the lowest is shown in gray. We see in the survival differences that the different values of the B parameter that controls the rate of increase in mortality have much greater impact on survival with, for example, the lowest survival in the black line and the highest survival to the right with the gray line. Clearly, similar changes in the magnitude of each of these two parameters, A and B, have substantially different survival outcomes. Changes in the former much less consequential than changes in the latter. The next model to be considered is the Makeham model, also known as the Gompertz-Makeham model. It purportedly represents an improvement in the Gompertz model. That is, Makeham found that overall mortality levels could be better represented if a constant term was added to the Gompertz formula to account for causes of mortality not dependent on age. That is, for example, accidental deaths. The Makeham survival model includes the product of the constant C and age X. The fourth model is the exponential model, which is effectively the Gompertz-Makeham model minus the Gompertz component. This model accounts for only accidental deaths C, and thus assumes age-independent mortality. Because mortality is constant with age in this model, its plot is simply a horizontal line intercepting the y-axis at C and extending to the right. The survival function for this model decreases exponentially with age. Whereas the De Moivre, Gompertz, and Makeham models were derived in an actuarial context, the next model we consider, called the Weibull Model, was developed in the context of reliability engineering. This model is a generalization of the exponential model, but unlike the exponential model, the Weibull model does not assume a constant hazard rate and thus has broader application. This model has two parameters. Parameter A determines the location along the age axis, and parameter N determines the shape of the distribution curve. Here I will show different values of these two parameters and how they affect the respective location and shape of the death distribution dx. Here we have age on the x-axis and the distribution of deaths dx on the y-axis. Different values of the location parameter A shifts the mean and the range of the death distribution along the age axis, but does not change the overall shape. In contrast, the shape parameter N can shift the location, but more importantly changes the shape, ranging from narrow to broad distribution. So the combination of parameters A and N in the Weibull model have the potential to allow this model to be fitted to virtually any observed death distribution, whether it's in humans as well as in non-human species. This adaptability is one of the main strengths of this model. A sixth model in this mortality model overview is the Logistic Model. This model was first introduced to demography by Pearl in 1920, who used the model to estimate not mortality, but the ceiling of the U.S. population. This model assumption is that the mortality reaches a plateau. Therefore, the rate of increase in mortality slows at the advanced ages and eventually levels off. This creates a long tail in survival. Both G and N in the parameters in the model control the shape and location. The last model I consider is the three-parameter model of mortality introduced by Siler as a competing hazards model. Siler added a third component to the Gompertz-Makeham model to represent the early life segment of humans. Siler called his model a competing hazards model precisely because he interpreted its three components as sets of risks that compete simultaneously throughout life. Parameters A1 and B1 control the scale and rate of change in infant mortality. Parameter C is age-independent mortality, and parameters A2 and B2 control the mortality scale and trajectory in young, middle, and old age. I will finish this module by showing graphs of the age-specific mortality model trajectories for the different models or groups of models, as well as the trajectories of survival and deaths. The first and simplest is the exponential model with constant mortality, as you see in the QX as a flat line, and that results in a geometrically decreasing survival and death trajectories. The next group of mortality models includes the Gompertz, the Gompertz-Makeham, and the Weibull, that shows the exponentially increasing mortality trajectory of QX and age patterns of survival and death. The shapes and details of these will depend upon the particular parameter values used in each of these models. The next model is the Siler mortality model. The unique and important feature of this model is the early infant mortality that in turn shows up as the early drop in survival and the early bump in deaths. The last model is the logistic type model, in which mortality slows and plateaus at the oldest ages. This plateau in mortality results in a long tail in both the survival and the DX schedules at the oldest ages. This completes the module 3.5 on mortality models. There are a number of other mortality models besides the ones I covered here that are referenced in the Princeton book on biodemography, as well as any number of the mainstream books on demography.